All right, so this week we're thinking about black holes and kind of completing our study of the end states of stars, where they end up. All right, so what is a stellar end state? What do I mean by stellar end state? Well, it's the final stage of a star. So it's gone through the main sequence. If it's a low mass star like the sun, it's gone to a red giant phase and planetary nebula, and then eventually it will end up as a white dwarf. That's the end state of a star like the sun. For more massive stars, they can become neutron stars, and they go through type 2 supernova. So they explode. They send a lot of their material out into space, but then there's still enough mass to collapse. And too much, in fact, that electron degeneracy pressure can't support the star. And they collapse until the neutrons can push back. And so their hydrostatic equilibrium is supported by neutron degeneracy pressure. So we have kind of the low mass and then the high mass, but what about the really high mass? What happens if a star has enough mass to even crush a neutron? At some point, there will be enough mass to do that, right? Everything has a breaking point, and a single neutron, will have a breaking point. If a star is massive enough, it can overcome that neutron degeneracy pressure. Beyond that, we don't know of anything else that can push back. So we've gone from nuclear fusion, that radiation pressure. When that goes away, when the star is no longer able to burn nuclear fuel, it collapses down, and then the electrons maybe can support it. And then when those get pushed inside of the atoms, creating all neutrons, and those get crushed, well, there's nothing left. There's no other things that we know of that can support the weight of a star. So at that point, what we believe happens is that it just keeps collapsing. This is really gravity's ultimate victory. It just collapses into a single point, which we call a singularity, a single point in space that has a tremendous amount of mass, and that is a black hole. Black holes are very weird, and I think you'll realize that as we learn some things about it and the way it affects the physics of space and time. All right, so the first big point about massive stars like black holes, and even a lot of this will apply to neutron stars and white dwarfs, is that they have very, very strong gravity. Okay, so let's come back to the Earth for a second. We're stuck to the Earth because of gravity. If we send an astronaut up to the moon, the gravity there is weaker, and so we can see the astronauts kind of bouncing around on the planet. They feel lighter because the gravity is weaker. It's actually about 1/6 of Earth's gravity. So what affects the gravity of an object? More mass, smaller radius. So denser means stronger gravity. Okay, so the more dense things have stronger gravity. The closer you can get to a high concentration of mass, the stronger gravity will be. So neutron stars are going to have more gravity than a white dwarf. And black holes must have the strongest gravity of all because you're collapsing all of that mass into essentially zero radius. But we can make this a little bit more quantitative. Okay, so let's think about quantitatively the gravity of a white dwarf and a neutron star. And we're going to do these calculations with the idea that Earth's gravity is equal to 1. So we're measuring everything relative to the Earth. So if I look on the screen over here, this is the general formula that I'm using. This would be the gravity number, what I'm calling the gravity number. This is the mass of the star, and this is its radius. Okay, notice that that's squared. All right, so for Earth has a mass of 1 because we're measuring everything relative to the Earth, and a radius of 1, so 1 over 1 squared is 1. So Earth's gravity is effectively 1. Well, how about a white dwarf? Well, a white dwarf is as massive as the sun, which turns out to be 330,000 times more massive than the Earth. But its radius is about the same, so its radius is still 1. Well, this math's easy. 330,000 divided by 1 is just 330,000. So the gravity on a white dwarf is 330,000 times bigger than the gravity on the Earth. Okay, so it's hard to really fathom what that means, but you can take that to mean really a lot stronger gravity on a white dwarf star compared to on the Earth. And when you go to the neutron star, it just gets worse or better, stronger, bigger, whichever adjective you like better, but definitely bigger, because its mass is bigger. Now, a neutron star, after it's gone supernova, there's still usually left like 2 times the mass of the sun, maybe up to 3 times the mass of the sun that's there. But let's say it's 2 times the mass of the sun, so it's double the mass, so 660,000 times more massive than the Earth. And its radius is only like the size of a city. Okay, so this number might not seem to make a whole lot of sense right now, but this corresponds to a radius for the neutron star of about like 10 kilometers, something like that. So if you take that 10 kilometer radius and compare it to the Earth's radius, you get 0.0016. So it's much, much smaller than the Earth. And so this number, so if you're dividing by a really small number, you get a much bigger number. And this is the result. 260 times 10 to the 9th. 10 to the 9th is a billion. So it's 260 billion times stronger gravity than there is on the Earth. Okay. So the gravity is almost getting exponentially larger as we go from a white dwarf to a neutron star. So what about the black hole? What happens with the gravity of a black hole? Well, the formula depended on the radius. What if the radius is 0? You can't divide by 0. Or if you do, you get an infinite answer. So that means the gravity of a black hole would be infinite. But also, technically, there's no surface to a black hole, because if the radius is 0, there's no surface there. There's nothing, no boundary. Well, there is a boundary, but we have to think a little bit more before we can talk about the boundary. All of the matter is believed to collapse into a singularity, so there's no surface to speak of. The gravity essentially gets infinitely large the closer you get to where the mass is located at the singularity. There's no limit to how big the gravity can be. But there is kind of an artificial boundary around the black hole, and I want to talk about that in the next slide. But before I move on, I haven't mentioned what this picture is yet, the background on all these slides. This is actually the first ever real picture taken of a black hole. It was taken in 2019, so very recently, and it's the black hole that resides at the center of the galaxy M87. It's kind of a blurry image, but keep in mind that this was taken of a galaxy outside of our own galaxy. So the fact that we could see any detail at all in it is pretty impressive. And all of the little features, like how it's a little brighter here and a little brighter here, and these little different color patterns, all of that, it turns out, is confirmed by our modern understanding of black hole physics. And when you get to watch the movie Interstellar, you might be able to imagine that some of the features of the black hole in that film will look familiar to this picture right here. Even though this is a blurry version, and that one's kind of a very high-tech artificial rendering. Okay, back to the story at hand. So we want to understand what black holes are like, and I was mentioning that they have a boundary. Now, to get to what that boundary is, we need to think about the strength of gravity in a slightly different way. So before I was kind of saying how it compares to how strong gravity is here on Earth. But there's another quantitative way to look at this, and that's the concept of escape velocity. So the background here is a space shuttle blasting into space. In order for it to leave the Earth, it has to go fast enough to actually escape Earth's gravity. Now, maybe I should have taken a different picture because the space shuttle didn't actually leave Earth's gravity, it just went into orbit. In order to leave Earth's gravity, like say to go to the moon or to blast off and explore the outer planets, the shuttle would have to go at least 25,000 miles per hour. Right? That's how fast you need to go in order to escape from the gravitational pull. If you don't get going faster than that, gravity will eventually slow you down and turn you around and pull you back to the Earth. Just like if you threw a baseball up in the air, the faster you throw it, the farther it'll go, but they always come back down, right? You know, everything that goes up comes back down. That's true until you hit the escape velocity. When you hit the escape velocity, it'll just keep on going forever. So now we can think about what would the escape velocity be for a black hole. To be a black hole, the escape velocity has to reach the speed of light, which is 186,000 miles per second. Okay, not miles per hour, miles per second. Once you've reached that escape velocity, no light can leave the star. And that's why we call it a black hole, because light cannot even escape from it. When light tries to leave the star, it gets pulled back down. Now, if you want to question this and say, well, why is light being pulled by gravity? I have to just say, trust me on this, and we'll come back to that in a few minutes. But light is affected by gravity, and it can be pulled back down. And unless or if the black hole, or if the escape velocity is the speed of light, then not even light can be going fast enough to escape the pull of the black hole. All right, now this gives us a way to define a boundary for the star, because technically anything could become a black hole if its mass was crunched inside a small enough radius. If you made it dense enough, you would get a black hole. You could take the Earth. You could grab a pen in front of you. If you could crush that into a small enough point, it would be a black hole. Now, that radius, that critical radius that you could crunch it down into, is called the Schwarzschild radius, and that's this variable right here. RS is Schwarzschild radius. It's an imaginary line, or it defines an imaginary line, and that imaginary line is called the event horizon, which might be a term that some of you are familiar with, have heard before. That is the imaginary line around a black hole, right? So it's this imaginary line in space at the Schwarzschild radius, and it's kind of the boundary of the black hole. Inside the Schwarzschild radius, the escape velocity would be greater than the speed of light. Outside of that, it would be less than the speed of light. So light can escape outside of the event horizon. It cannot escape from within. To calculate what that Schwarzschild radius would be, we have this approximate formula here. So this is an approximation. I just made a round number here of 3 kilometers. So if m here is the mass of the star, so if the mass of the star was equal to the mass of the sun, its Schwarzschild radius would be 3 kilometers, because this would be 1. So how would you make a black hole out of the sun? Well, you would have to collapse it down so that its radius is less than 3 kilometers. Luckily, its radius is much bigger than that, and so it's not a black hole. But technically, you can use this formula for anything, any object at all. Take its mass, divide by the mass of the sun, and multiply by 3 kilometers, and that will tell you how small it needs to be crunched down in order to make it into a black hole. All right, so you might have some questions about what's going on. What happens inside the event horizon? What happens outside the event horizon? Let's take inside first. This because it's easy. I have no idea, and no one really has any idea what happens inside the event horizon. And there's a very good reason for that, and that's it's impossible to know. Because light can't escape it, information can't escape it. So we can't learn anything about what's happening inside the black hole. Keep in mind, everything we learn in astronomy, or essentially everything we learn in astronomy, is from the light that we take from the things we're looking at. You can't get light out of a black hole. You can't learn what's going on in there. You can't do any spectroscopy or any of the neat things that we've talked about. So outside the event horizon is where we can make some progress. And there's a few things that will stand out. One, the gravity is very strong. So outside the event horizon, gravity is very, very strong. And then space is very curved. Okay, so that's something we'll have to explain more. And in addition, time is very slow. Those are not straightforward things, but they're the essence of what's happening around a black hole. Space is very curved. Time is very slow. And I'll need to explain about what I mean about those things. So to understand all of this, how do we make any sense out of what I'm saying here? We have to learn about the theory of relativity to get any further. All right, so we'll start with the principle of relativity. There's a lot of writing here, but this is actually a very simple concept, especially compared to what we're about to do after it. The principle of relativity is just that every observer, every person, has a frame of reference. And the laws of physics are the same for every observer, but your perceptions of things can be different. Okay, so this is pretty straightforward and non-controversial. The example on the right, I think, illustrates this pretty well. Suppose you're standing on the side of the road, your friend passes by in a train. The train passing by is an event, right? It's something that happens at a location and at a time. In your frame of reference, your friend is moving, you are stationary. In your friend's frame of reference, the opposite is true. You're moving and they're stationary. And in fact, when they're in the train, they probably don't feel like they're moving at all. Now, when they look out the window, they see motion relative to the surroundings. But if you closed all the windows and you were in a train and you were moving at a constant speed, you don't actually feel like you're moving at all, even though you might be moving very fast relative to the ground. So this brings in the idea that people can disagree on speeds, on each other's speeds. I can say you're moving, you can say I'm moving, and vice versa. All right, so this is the principle of relativity, and it was first recognized in 1632. So this is a long-standing idea in science. No one made too much about it for a long time. It didn't come up very much. We kind of took it for granted, accepted it. Yeah, of course, that's true. But then Einstein came along, and he had a new take on relativity. And it's sort of simple to put forward what he proposed, but the implications of that are what are really kind of mind-bending. So this is 1905. Einstein did kind of an amazing number of things in 1905. He published 3 papers, one of which won him the Nobel Prize, one of which kind of started the field of quantum physics, and the other one was about relativity. So it's usually referred to as his miracle year, 1905. We're only interested in one of those things for right now, and that's what he contributed to the theory of relativity. So he postulated that light always has the same measured speed, independent of the observer. Let me pause for a second for you to think about that. Light always has the same measured speed, independent of the observer. That's not common sense, right? That might seem like a straightforward statement, but it's not common sense that would be true. In fact, it's direct opposite for what you would think. As we showed in the last example, speed is always relative to the observer, right? We measure things relative to ourselves. But it just so happens that he's right, that light is different in a very special way, and so this is called the special theory of relativity. It applies to any observer moving at constant speed, and observers moving at constant speed are called inertial observers. All right, so let's think about this a little bit more. Why did he postulate it at all? Why did he come up with this? Where did this come from? Well, to understand that, you have to know a little bit about what light is, which we do. We know it's an electromagnetic wave. And it propagates through space because there are electric fields changing and magnetic fields changing, and they sort of build upon one another. One causes the other, and they work together to propagate the wave forward. So he knew all this, and he knew the equations that describe them. And he also knew that the equations give light a specific speed. This number right here. But they don't say what reference frame that speed is measured in. So he thought about this some more. I should mention that no one else at the time had any issue with this. It was only Einstein that was thinking about this problem. And he said, well, what happens if I was riding along a light beam? So I'm going the same speed as the light beam, and I look around, what do I see? If I'm going the same speed as the light, then the electromagnetic fields are not changing because I'm moving along with them. They're constant. But then how do I describe the physics of why they exist at all? Because if in my frame of reference there's no changing electric fields, then there's nothing to create the changing magnetic fields, and vice versa. So it was a paradox. And his solution to that paradox was that, well, you just can't do it. You cannot travel as fast as light. Because if you did, and you looked around, you would have to violate the laws of physics to have light be there. And then he took it further and said that what these equations are telling us is true. They're not making any reference to a specific reference frame. They're not specifying the speed of light is this measured relative to whatever. And so he concluded that all reference frames have to be equally valid. And in all reference frames, light has this same exact speed. You can't catch up to light. And its speed is never any different. As fast as you want to go, light is going to be going 3 times 10 to the 8th meters per second relative to you. If I'm stationary, it's 3 times 10 to the 8 meters per second. If I'm in a spaceship, it's 3 times 10 to the 8 meters per second. There's nothing you can do to change how fast light is moving relative to you. Okay. So I want you to understand like how crazy this is, how crazy of an idea. So let's take this example. Imagine your friend's riding a bike at 25 miles an hour. You run after it at 10 miles an hour. The bike's still moving away from you at 15 miles an hour. All right? If you got in a car and drove 40 miles per hour, you could eventually catch up with the bike. This is just all principle of relativity stuff, right? The speeds are relative to one another. If something's moving a certain speed and I move faster, I can catch up to it. What Einstein is saying here in this theory of special relativity is light does not follow these rules. Okay, it's different. There's something different about it. When you speed up, light speeds up too. It's a crazy idea, and pretty much everybody thought it was a crazy idea, even at the time. But it's a crazy idea that turns out to be correct. So we have to think about what the consequences are. Now, I'm not going to get into the details of this, like the mathematical details of this, but I want you to know about some of the qualitative consequences of the speed of light being constant. And the most interesting one to me is time dilation, that people's measurements of time are actually different when they're in different frames of reference. And it happens when people, objects, things are moving faster, time slows down more. Their clocks tick slower. Less time elapses for them than for people who are moving slower relative to them. So in the picture on the right, we have a person and another person. One person is stationary on the Earth. The other person goes off in a rocket ship. Because she's moving fast, or we presume she's moving fast, her time ticks off more slowly. So when she goes to return, maybe only this much time has ticked off. But for him, a much larger amount of time has ticked off. And it's theoretically possible that she could go fast enough and far enough that when she came back, she would be just about the same age and he would be an old man. Okay, relativity gives us these very, very strange consequences. Time, our whole concept of time depends on the speed that we're moving. Now, I should say here that for each of these people individually, things appear totally normal, right? It's not like you feel like you're moving slow when you're going fast. It's not like that. You perceive everything, experience everything just like normal. It's only when you return do you see a big difference, right? You see, whoa, that person's really old now compared to me. I haven't aged much. What could have happened? We don't have an intuition for this because we never move fast enough. Fast enough means close to the speed of light, and we have never been able to go anywhere near the speed of light. So these effects have stayed hidden, or they did stay hidden for most of history because they just never came up. It was never something that was going to reveal itself to us in the natural world. But we have been able to verify this for things like elementary particles in physics labs. We've been able to see the effects of this time dilation happening. All right. Now, this is all to do with how fast something is traveling. But the theory depends on objects moving at constant speed. That's not quite the scenario we want to understand in order to think about black holes. Because black holes are strong gravity. That means they're going to accelerate objects quickly. Their speed is going to be changing fast. We need a more complete theory. And Einstein developed that about 10 years later, and he worked on it continuously. So after he published the special theory, he worked continuously for the next decade until he finished the complete theory, which is called the general theory of relativity. And that accounts for accelerated frames of reference, what we refer to as non-inertial observers. So you've got the inertial observers now and the non-inertial observers, constant speed and acceleration. Kind of any kind of motion that you could have is now included in the theory. The key idea in this theory is something known as the equivalence principle. And that is that free fall is equivalent to zero gravity. Okay, so almost everything in this theory follows from that simple statement. Free fall is equivalent to zero gravity. I promise we're going to connect this all back to black holes before too long. All right, so what does the equivalence principle really mean? It means that any experiment that is performed in a free-falling reference frame would have the exact same results if it were performed where there is no gravity. Okay, so you cannot do an experiment in a free-falling reference frame that will distinguish between that and a place where there's no gravity. Everything would happen the exact same way. So imagine you had a person in an elevator. We can think of 4 different scenarios. The elevator's stationary. The elevator's kind of accelerating down. It's accelerating up. Or the cable has been cut and it's in free fall. So this is free fall. Well, in these cases here, right, lighter than normal, heavier than normal, the person's weight is going to change. Right? If you're ever in an elevator and have a scale with you, throw it on the ground and see what happens. But when the elevator goes down, you'll be lighter than normal. When the elevator goes up, you'll be heavier than normal. That's an experiment. And that experiment tells you which of these reference frames you're in. So experiments can reveal your reference frame. What the principle of equivalence is saying, or the equivalence principle is saying, is that this free fall reference frame, where you have no apparent weight, you would have no apparent weight in free fall, you'd be weightless, is the same as if you were in totally empty space. So even though you're falling to the earth because of gravity, your weight and consequently the results of any experiment you conducted while you were falling would be the exact same as if you did those things in zero gravity in totally empty space. All right, let's take another example. Two people playing pass. All right, so this is a very weird version of two people playing pass because they're playing pass while they're falling down a interminable hole. But it's a good illustration of the idea. So as they're playing pass, how do they throw the ball back and forth to one another? Because they're all falling, and because of the equivalence principle, this free fall situation is exactly as if they were in purely empty space. So you can ask, how would we play pass in purely empty space? In order to make the ball go from one side to the other, you would just throw it directly to the person. That's it. So in free fall, that's the same thing. You would just throw the ball directly at the person, and it would get there. And it would get there because you're all falling together. You, your friend, the ball, they're all falling together. Now, if you were watching this from Earth, the ball would go this weird curved path and then this weird curved path. But in the frame of reference of the people who are falling, they're falling together. So they're always eye to eye. And the ball is just going back and forth in straight lines. Okay? It's just as if they were in purely empty space. Okay. Now, this idea can help us understand a little bit more about what gravity is. And so let's take the idea of an orbit, like astronauts in orbit around the Earth in a satellite or in a spaceship. The Earth is in orbit around the sun. The moon is in orbit around the Earth. Any type of orbit. Long before Einstein, Isaac Newton showed that orbits are really just a manifestation of gravity. It's free fall. Something in orbit is in constant free fall. Okay, so Newton made that connection. Einstein's principle of equivalence is extending that another step further. Okay, so ultimately now what we can say is that orbits are free fall caused by gravity. So thank you, Isaac Newton. And free fall is the same as being with no gravity at all. Okay, so that's thanks to Einstein. And that's sort of the modern understanding of what gravity is. Orbits are free fall, and free fall is like no gravity at all. Okay, so it's almost like an orbit is no gravity. Okay, we need to come back to black holes. What does any of this have to do with black holes? Well, they have to do with black holes because of the way the equivalence principle affects light, or the way it applies to light, and what it reveals to us about the fabric of space itself. It gives us a new way to think about what gravity is. So let's look at this example. You're on a spaceship and you're in totally empty space, no gravity. You want to shine a flashlight to the front of the spaceship, so you just shine a straight line to the front of the spaceship. Okay. But now imagine the spaceship is in orbit. Okay. The equivalence principle says that there's no experiment that I can do that can distinguish between my orbit and purely empty space, because an orbit is free fall. So that means in orbit, I would also aim the flashlight towards the front of the spaceship. But now think about it viewed from the Earth. If the person aims the flashlight this way, later on, the spaceship's going to be pointed a different way because it's moving around in a circle, right? It's moving around in orbit. So you would think that if light is going to just take a straight line path and you shined it in this case, it would head off in this direction. The spaceship would move away and would sort of hit the side of the spaceship over here and not the front. But the equivalence principle says it has to hit the front. The only way that can be true is if light is also curved by gravity. So you're over here, you shine the flashlight this way, the spaceship curves away, the light has to curve away as well. So light does the same thing that the basketball did in the example a few minutes ago, right? Light is curved, the path of light is curved by gravity. But we still want the idea that light always travels in space lines. So there's another way to think about it, and that's that mass, or gravity, causes the space around it to be curved. And if we look at it that way, then light is just traveling in a straight line around curved space. It's almost like, or it is like, the Earth is a source of gravity deforming the space around it. And something in orbit is not being like tethered by a rope. It's more like following along a curve in space itself. All right, so that's how we get back to black holes. Because black holes are these extremes of gravity, and now we know gravity curves the space around it. What is curved space like? All right, so this is a helpful picture. We have a rubber sheet. We have an ant crawling on a rubber sheet. And this would be like flat space. It travels a straight line no issue. You add a star or a massive object onto the rubber sheet, it's going to deform the sheet or deform the space around it. For the ant to go from one side to the other, it now has to travel this curved path. Well, we are like this ant. We're confined to the rubber sheet. The rubber sheet is the space around us. And so the ant travels a curved path. It goes down into the sheet and then back up the other side. That's its version of a straight line path. It's the only straight line path it can take. So how about the curved space around a black hole specifically? Well, we can build our way there. The sun deforms the space around it a little bit. The white dwarf deforms it a little bit more. Neutron star even more. And a black hole deforms it so much that it just really drops out to nowhere. There's no end to this. At a certain point, there's an event horizon, so something could fall to the point of the event horizon. Then beyond that, we just can't learn about what's happening. But in theory, it just goes on forever. It's space that has become infinitely curved. Okay, and because it's infinitely curved, this path is like infinitely long, so it takes light an infinite amount of time to get out. In other words, it can never get back out. Well, at this point, if you're thinking this all sounds kind of wacky, I should probably give you some evidence that it's correct, that there's a reason to trust it. So the theory was proposed, this general theory of relativity was proposed in 1916. A couple of years later, a guy by the name of Arthur Eddington measured the light from a star that was behind the sun during an eclipse. So the positions of stars are all mapped out really well, and they had been for many years. So we knew where this star was supposed to be. But Einstein's theory says that masses like the sun will curve the space around them. And so that means the path of the light from stars that are around the sun or from behind the sun will have to take a curved path. So the star is off in this direction. Its light is coming to us from here. The space around the sun is curved, and so the light gets deflected. Now what this does is it acts like a lens, so we call it gravitational lensing, because it bends light, almost like a lens focuses light. And so Eddington's sitting here in 1918. He waits for an eclipse, because if it's not an eclipse, then you can't see the stars that are to either side of the sun, because the sun's light is too bright, obviously. So he waits for an eclipse, and he sees this star, this particular star, off in this direction, so this apparent direction, which is not where it was supposed to be. And he was able to measure the exact amount that it was different, and it was the exact amount that Einstein's theory had predicted. So this was very good confirmation that Einstein was correct, that matter, like stars, bend the space around them, and light travels in that curved space. All right, so a while back I said time is very slow around a black hole. And we've covered the gravity is very strong and the space is very curved part. But what does it mean to say time is very slow? That sounds crazy. Well, we did get the idea of time dilation from special relativity. There's also a time dilation that happens due to gravity. And we have a different name for it. It's called the gravitational redshift. So the note here, it's called gravitational redshift because of how light is affected. You slow down time, then the frequency gets slower, the frequency of light get slower, but the speed of light is going to stay the same. So that means the wavelength has to get longer. Therefore, the light is redshifted. Okay, just like the redshift that we've encountered before. Well, similar to the redshift that we counted before. This is a different thing. It's called the gravitational redshift. We have detected it many times. The first time was in 1976. The Viking mission had sent a satellite out, and that satellite happened to be on the other side of the sun. So we knew about how far away it should be and how long it should take the signal to transmit back and forth between the satellite and the Earth. And knowing Einstein's theory, we could predict how much longer that signal should take because the light had to travel the bent path, the curved path to go around it. Instead of just, taking the straight line route from here to here, we get the signal. It had to bend around the curved space of the sun. And the measurements matched exactly what the theory predicted. Okay. A more modern example of this is our GPS. We are down here on the Earth using our GPS to navigate around. That navigation relies on communication between the satellites that are up in space, thousands of miles above us. Well, that's a much weaker gravity field than we have down here. What that means is that our clocks here on Earth are actually running a little bit slower than the clocks are running up in the satellite. If they didn't account for that, we wouldn't be able to have the precision necessary for GPS measurements. That small time difference would lead to massive errors in the positioning. So the GPS satellites have to sync up with the clocks on the Earth. There has to be a conversion between the reference frame of the Earth and the reference frame of the satellite. So this gravitational redshift is a very, very real thing. How slow is the time near a black hole? Well, that depends on the details. The math of this can get very, very messy and complex. Black holes can have different masses. They can be spinning or not spinning. They can have electrical charge. We're going to just think about the simplest possible case. A black hole that's not spinning at all is just a straight black hole sitting there, not doing anything else. In that case, this equation here describes how you could translate between the time for someone, as measured by someone near the black hole, to the time for an observer this far away. So that's t infinity, meaning like infinitely far from the black hole, and then t is somewhere near the black hole. Rs is the Schwarzschild radius, so where's the location of that event horizon? And r is the radius of the observer that's near the black hole. So you plug in the numbers into this calculation, and you can convert between the two times. So one thing I want to notice first, what happens if the radius of the observer reaches the Schwarzschild radius? So this is Rs. Then you have Rs over Rs. 1 minus 1 is 0. And the time for the observer goes to 0. Okay. No matter what time elapses for the person far away, 0 time elapses for the observer near the black hole. That is time coming to a stop. At the event horizon of a black hole, time comes to a stop. Okay. Now, if you move away from the black hole, right, R is getting bigger. So R is bigger than Rs. So this number is less than 1. So this number here is going to be slightly less than 1. Okay. And then the time here is going to be less than the time here. Okay, so it might help to put some real numbers in. So let's say you go for lunch near a black hole. You hop in your spaceship, fly out to a black hole. You want to have lunch near a black hole and see what it's like. So what will it be like? So let's imagine that you're sitting at 1.1 times the Schwarzschild radius. So you're like 10% beyond the Schwarzschild radius. You're outside of the event horizon for 1 hour. How much time is going to elapse back home on Earth? So the time for us, or for you eating lunch by the black hole, is 1 hour. T infinity in this case, the time very far away, is the time on Earth. Okay, so I've changed it to TE for Earth. Radius that you go to is 1.1 times the Schwarzschild radius. And we can cancel the RS's. You calculate what this number is. Take 1 hour and divide by that number, and you'll get 3.3 hours. So if you go hang out 1.1 times the Schwarzschild radius of a black hole for an hour, and then you return home, you will have been gone for an extra 3.3 hours, or I guess an extra 2.3 hours compared to what you thought. Right? 3.3 hours will have elapsed back on Earth, while only 1 hour has elapsed for you. Okay, so this hopefully illustrates the weirdness, the strangeness that black holes have revealed for us about nature. The gravity is really strong, and because the gravity is really strong, space is very curved, and that leads to this idea of gravitational redshift, that time is actually affected. Time runs slower when you're in strong gravitational fields, and in fact, it stops when you get to the event horizon of a black hole. What happens inside the event horizon? Anybody's guess. But at the event horizon, time comes to a stop, and it gets very, very, very slow as you approach the event horizon. If you were to fall into a black hole, it would essentially take forever to get there. Now, for you, it would probably be a very bad experience, because one thing I don't really talk about in here, but that is an important consideration, is that tidal forces are actually very, very strong near a black hole, because the gravity changes so rapidly as you get close to black holes that the tidal forces, the forces kind of on one side compared to the other, are so strong that they would rip most things apart. Okay. When you watch the movie Interstellar, I believe they make reference to tidal forces and their effect on things. When you watch the film, hopefully you can look out for that. Astronomers have a kind of funny word for what happens to things when they approach a black hole, and that's spaghettification. So if something gets really close to a black hole, the tidal forces will stretch it out as if it were a strand of spaghetti. So you have very high physical effects that happen near the black hole, and then also these time effects, the gravitational redshift that are happening in the vicinity of a black hole. They're very, very strange objects. I find it fascinating to think about them and to talk about them, and hopefully this lecture will help you appreciate what they talk about and what they go through in the film a little bit more. One more slide on this, and that's sort of a look towards the future, and that is about gravitational waves. So this is not specific to black holes or anything. Any massive object that's moving through space would be predicted to create waves in the fabric of space, and these are called gravitational waves. Einstein knew about this idea, but the experiment to find them, to detect them, was very, very hard to do. And in fact, the first detection wasn't until fairly recently, 2015. I can remember I was teaching, I think it was either my physics class or the astronomy class at the time when they were about to make the discovery, and I stopped the class. We actually watched the introductory press conference where they announced the discovery, because I had been kind of anticipating this for a lot of years. There was lots of different iterations of experimental ideas. How can we detect these gravitational waves coming off of things? And I believe that the instrument has to be so sensitive that over like the mile long stretch that their laser interferometer goes, they needed to be able to measure changes in the length down to like the width of a single proton. And they were able to achieve that level of precision. And there's three separate facilities that were able to detect the measurements of this one event back in 2015, all simultaneously. Now, this is their data. It might look like a bunch of wiggles, but those wiggles carry a lot of information, and the overlap between them and the fact that they look exactly the same was confirmation of the theory about gravitational waves. And what they were able to do is figure out what these wiggles mean. And what they appeared to mean is that two black holes had swirled into one another and merged. So this wiggle pattern is what it looks like when you get gravitational waves off the merger of two black holes. So I expect a lot to come from this area, that this will actually open up a new window in the universe. We have our electromagnetic spectrum, and that's expanded over time, going from visible to then all the invisible types of light that we can see. Now maybe we can learn from gravitational waves that are coming to us from distant objects in space, things like black holes. All right, so we're not totally done with black holes. We will come back to them again as we talk about galaxies, because it turns out that at the center of every single galaxy, there is a black hole.